Hello friends, today's session is on geospatial analysis using Python, working with raster data. My name is Prasun Kumar Gupta and I am with IIRS ISRO here at Dehradun. So let us first try to understand why we need to do geospatial analysis using a programming language. There is no dearth of softwares in the market today. Why should we look at a programming language to do the analysis that we can simply do by a click of a button? Why do we need to write some code? So, the first point here says contemporary proprietary softwares have limited functionalities. The current softwares that we have, especially the proprietary ones, the paid or licensed ones, they have a limited set of functionalities. The ones which we are already exhausted with, we are completely utilized them, and they are not suitable for newer things like process based modeling. Till now we are doing empirical modeling, we're using certain coefficients, regression, all that is statistical or mathematical in nature. But now when we talk about physics based models, when we talk about understanding the process and trying to emulate the process, these softwares are not enough and they cannot do it. So we need a different approach. A second and very important thing is now there is a convergence of technologies happening. As you know that artificial intelligence, big data, internet of things, IoT, and all this are coming together with remote sensing and GIS. And so we need a new paradigm, we need a new set of tools which can help us do all of this together. We cannot think of connecting a Raspberry Pi to ArcGIS. Uh, it has not been done, or there is no use case of that. Possibly it could have been, but we need to rethink our approach of doing spatial analysis. Conventional softwares, traditional softwares are not enough. Third point is, if you are into research, if you are thinking of making progress in this field, discovering new things, it is unthinkable using the current softwares, especially since large amount of softwares are coming, large amounts of data is coming. We are in the era of big data. Earlier we used to get one data set every 16 days or something. Now we have one high resolution data every half an hour. So we are in the middle of a big data problem. It is not going to come. We are there already. And if we are still using standalone on my desktop softwares, then we are left behind. We must adapt programming to be relevant, to be contemporary in the field, and we have to progress in the field. And this can only be done using a programming language. And because there is a large number of libraries, because there is a big ecosystem, there is a large number of users, lot of help available on the internet, lot of courses on the internet, uh, using Python programming language. That is why we have chosen Python as the language of choice for doing geospatial analysis. The same thing can be done on C++, Java, all these popular languages also. The idea here is that Python is an easy to use language. For a newcomer who has not learned programming much, Python has a more gentle learning curve as compared to C++ or Java, which has a steep learning curve. It is difficult to uh, first be good with the language and then become good with the geospatial part of it. So Python makes things little simpler. So because of these reasons, you must adapt or learn Python and do try to do all your analysis uh, using remote sensing data, using GIS data, using field data on Python. So as I told you, the geospatial ecosystem in Python language is very big. This is a screenshot from their website called pypy.python.org. Let me open and show that to you. So The package, it is a package repository, the official package repository. Many people, even you and I, can make new packages in Python, but not a lot of people put it on this page, which is the official Python package index, PYPI, as it is called. And if you look, there is you see there are about 4 lakh projects, and these projects have a wide range of topics, starting from sorry starting from communications, conferencing, etc., file sharing, databases, desktop, gaming, internet, multimedia, finally coming down to scientific and engineering, AI, astronomy, chemistry, hydrology, image processing, and so on. So if you click on GIS, you will see that there are currently 993 packages only for doing GIS in Python, and they are very popular and currently up to date. So you see today, September 22nd, also many packages are being updated. The Earth Engine, which is a very popular tool nowadays, the Python API has been updated today. So all these is happening in real time today, and you must adapt it if you want to remain ahead of this field. Also, we saw hydrology as an example. Let's take that and see what we get there. So it says there are about 139 packages which are labeled as hydrology. So there is a coast ocean assessment tool. There is a river camera observation locations. There are logger tools from the logging data you get from gauging stations, etc., and so many others. So lot of water balance tools, time series tools, and so on. So lot of Python packages are available. You should understand these packages and start working with them in Python. So today's session is on the raster side of it. As you know, GIS data are of two types: vectors and rasters. Vector is what we call as point, line, polygon, or most common file for types are shape files or KML files. Those will not be covered in this session. To work with those types of files, you have to use these set of packages: OGR, Fiona. Fiona is a nicer version of OGR. OGR can deal with many types of 100 plus different types of vector file formats. Fiona can deal with a less number of them, but the more popular ones like shapefile and KML files and all. And it has made all that low level coding little abstracted. So you can just write open file, read file directly instead of going into each feature and reading the geometry. And also, Fiona makes your life easier, but it is built on top of OGR. OGR is the parent library. Then earlier, about 5-10 years back, PyShape or Shapefile, this was a very popular package. It was very easy. There was a Google page on which you could see the documentation, and it had clear instructions to do. But now Fiona with integration with GeoPandas, integration with Pandas and Matplotlib and Cartopy and all these. So now it has become a more popular and easy to use package. GeoPandas, it can directly read your shape files, and it can plot also. It can do all your database based queries, do your spatial analysis. A lot of things can be done directly. Otherwise, you have to use OGR for reading it, Shapely for doing your geoprocessing, PySal for doing your statistics or spatial statistics, and so on. So you have to use different libraries. But now GeoPandas is a one good library which does all of them together. Coming to raster based, again, JIDAL is the parent library. JIDAL is the one which supports over 100, again 100 plus file types, and it is very low level coding. So you can go into individual pixels or individual bands, and you can work on each and every aspect of the raster file. Common raster file formats are TIFF and IMG, and you can you can go to the depth of the file and take out information. But most people don't require that. Most people need to just open the file, read the data, or do some transformation, or get part of the data. So Rasterio is another package which is built on JDAL. It is a more nicer, cleaner interface, and it doesn't have that all that low level coding is required, and it also does not support all file formats, only the popular ones like TIFF and IMG and all. OpenCV has been around for a long time. OpenCV is a package which primarily works with RGB data with only 3 bands. But now you can provide it more bands, but you have to specify which bands it will take. And it works on 8-bit data. So 0 to 255 is the maximum values that you can work with. But as you know, most satellite data or DEM or any raster data you use today is either 16-bit or floating point, and either integer or floating point in 16-bit or 32-bit even in some cases. So OpenCV in that case, it will resample the data down to 8-bit. So that way there is a small drawback, but otherwise OpenCV is a huge library, very popular in the machine learning community, and it has many functionalities to read the file, to perform transformations, to perform even things like face detection and all, so many filtering options. It's a huge library. So if your data is 8-bit and if you are content with 3 bands and things, OpenCV, you must look at it. Then there is one package called Raster Stats. A lot of times we need to do things like zonal statistics and all. So the ready-made functions are available in Raster Stats if that is what you're looking for. Then SkitImage. This is an offshoot of the skitlearn package. Skitlearn is a very popular package which is meant for machine learning tasks. So they have made a SkitImage package which has a lot of, again, similar to OpenCV, it has a lot of functions for transformations, filtering, and so on. Also, the inbuilt package in Anaconda, which is scientific Python, SCIPY, that also has a .image module, submodule, I can say, which also has a lot of image processing based functions built in. The last library that I want to talk about is PIL, that is Python Imaging Library, PIL, also called Pillow. This is a very popular package. It is very simple to use, very easy to use. If you have simple RGB images, like ones you take from your mobile cam or things like that, or from your field cameras and things. So if you want to do simple transformations, cropping and band changing or changing the data type or things like that, simple operations can easily be done in PIL. It's a very lightweight package also. So for simple tasks, I would suggest you go for PIL. But JDAL should be the package of choice when you want to know the in-depth about raster processing in Python. Now, Python is a very popular language also because it gets easily linked with legacy software. So legacy software means you have some old software which you've been working for over 10-15 years or 5-10 years, and you want to uh, have new functionalities, and the coder for that software is gone. You cannot get in touch with them and you cannot improve the software anymore. So Python has this advantage. It can create a port, like an interface between an existing legacy software and the Python language. So what is happening is all these popular GIS remote sensing softwares, they are now coming up with their Python functions. So ArcGIS came with ArcPy, which is the Python library for using ArcGIS functions. Then QGIS came with PyQGIS. Uh, Grass has a PyGrass. Grass is also a GIS software. QGIS is also a GIS software. Google Maps, the one which you use, Google Earth, Maps.google, they also have a Python package for Google Maps. And Earth Engine, which is the most popular today cloud-based GIS software, that also has a Python package linked to it. So you can install Earth Engine and get all the Earth Engine functionalities in your Python program also. So that way Python is very popular and it has a huge reach across the geospatial domain. Any software, any data type, any specific functionality that you want to do, first search whether there is a package linked to it in Python. So maybe you want to do hydrological modeling, hydraulic modeling, atmospheric modeling, land use, land cover change, anything. First check whether there is already a Python module existing for it, or if not only for that function, a bigger library which has one function to do that task. So all these packages are well maintained, they are up to date, they are continuously being updated. As you just saw on the PyPy page, Earth Engine just got updated today. So these packages get updated very fast. So, and they are well documented. A lot of documentation is available. If the document is lagging somewhere, there are Stack Exchange and Google groups and on these websites where you can get more and more information about each of these packages. They have these mailing lists, as they call it. So each package will have a maintainer, and all the developers will be on that list. So if you send an email, I am facing this problem, these are the steps that I have followed, and this is the expected solution, but I am getting something else. So they will be very happy to respond back and tell you how to do it correctly. Again, each of these are meant for a specific purpose. Okay. So if you want to simply read or write a file, a 8-bit file, you could simply use PIL if it doesn't have any georeference. But if you have a georeferenced file uh, which has 16-bit of floating point data, then JIDAL is the only option, or Rasterio is another option. So depending on what you want to do, you may have to select the appropriate library. But otherwise, all these packages are very good at what they do. So today in today's session, as you know, we will be focusing on JIDAL. Now, JIDAL and OGR, they were separate libraries earlier, but now they have been combined into a single package. Once you say conda install JIDAL, both JIDAL and OGR will be installed in your system. Again, to remind you, JIDAL is for raster processing, OGR is for vector processing. This we are not focusing on today. Okay, so we are focusing on JIDAL. JIDAL was made by this gentleman whose picture is on the slide. His name is Frank Warmerdam, and he first started. He is a very passionate programmer, especially in the geospatial domain, and he started contributing to various geospatial packages. Uh, and out of his passion, he started making this small library, which was the initial idea is that it should, or the idea of the software is that it should act like an interface between any sort of file and the GIS software. So it was meant to be a read-write interface. It can read any file type for GIS, and from the GIS, it can write it into an output file. So in 1998, the first version was released by Frank Warmerdam, and then a lot of people joined him. Today, he has the project. It is now taken up by OSGeo as its main project, and it has a very good, strong team of developers led by these three people, primarily Evan Walt, Howard Butler, and Marcus Nettler, and many other people who are selflessly contributing to this project. This is the website jidal.org. Let's go to the website also, have a look at what the page looks like. So, this is the page for JIDAL. As it says, it's a translator library. It is meant to translate data for GIS or among themselves. For geospatial data formats, it's an open source license, etc. Then there are different links. We will go to them individually. It's a OSGeo project, and OSGeo is the maintainer or the primary funding agency for this project. Uh, So it is under the MIT license. It is an open source project. The source code is available on GitHub. You can go to github.com/osgeo/jadal, and you will see that the source code for the entire Jadal package is freely available, primarily written in C++. Uh, 67% of the project is C++, 15% is Python, 13% is C, 0.8% is Java, primarily a C++ package. Okay. So as you can see, there are nearly 400 contributors to this project. It is very popular. It is the most popular geospatial package in this domain. Uh, and a lot of softwares are using it. So as I was telling you, it is MIT licensed. It's open source software, and it is licensed under a very permissive license. So what this JIDAL licensing means is it's also called a lesser general public license. There are in open source there are two terms: general public license and lesser general. General public license says that if a software is free, then it should always be free. It cannot be mixed with non-free software, or it cannot be mixed with software, or it cannot be sold or cannot be made money from. JIDAL is under the lesser general public license. It that says that uh, you have improved it or you have added some effort and you think you can uh, make some profit from it, you can sell it. So till I think ArcGIS 9 point something, ArcGIS used to write their own code for reading and writing data. After 9.3 or something, they also moved to JIDA. So if you are buying ArcGIS, you are actually in the backend using a free software called JIDAL to read and write all your data. So it is used by nearly 112 softwares, which they have listed in their website. So on the JIDAL website, there is a link called programs. If you go there, they will show you all the, not programs, sorry. I think it is softwares using JIDAL. Yeah, software using. So there is a link which says in their FAQs there is a question on the which softwares use JIDAL. So there's a huge bunch, right from all the packages like Fiona, GeoDjango, GeoServer, Ilvis, a Map Server, Map Windows, NASA's Whirlwind, OpenEV, PostGIS, QGIS, R, Rasterio, Saga. These are the open softwares which use JIDAL. These are the free of cost. But then there are proprietary or licensed softwares which people pay money for and actually is using a free software, just like ArcGIS 9.2 plus. So uh, after 9.2 onwards, they have moved to even ERDAS, FME, Google Earth, Idrisi, uh, and all these softwares. You'll recognize a lot of names: Skyline Globe and uh, Transcad, and so many softwares. They're all using JIDAL in the background. So JIDAL is a very powerful, very popular package, and you should learn it. Including all the popular softwares like ArcGIS, QGIS, or Google Earth, Grass, Idrisi, GeoServer, they all use JIDAL for reading and writing data. Now, Frank was earlier an OSS maintainer, then he joined Google in 2011, I guess. Yes, 2013, there's a blog post where he says that he's developing Earth Engine. And then later on, I think he moved to Planet, the company Planet Labs, which is making all these constellation of satellites to give you high resolution data every day. So he's a very busy man, and there is one guy, even Walt, who is a very busy and very prolific developer for the JIDAL project, and he has extensive knowledge about the entire project. And so yeah, this is a tweet about 3 years back. Niall Dawson, which who is a again a very prolific developer for the QGIS project, he has written in this tweet that this is a periodic reminder that if even world is ever hit by a bus, the whole spatial community is truly doomed, because on that one guy, so many people are relying. If the guy who's developing Jidal, if Jidal tomorrow is not there, or something is not being developed, then a lot of people who are relying on Jidal will face a lot of issues. So Jidal is important. It's a translator library for raster and vector data. Basically means that it helps you translate one file format to another file format. But that is not the only thing that it does. It does a lot of things, and we will see during hands-on what all the capabilities of Jidal are. It is licensed under XMIT and by OSGeo. The advantage of Jidal is that it presents a single raster abstract data model. Now, this may at first appear daunting. What does this mean? So, basically, this line means is that irrespective of the file type, if you're using GeoTIFF, if you're using NetCDF, HDF, any raster file format on earth, it will convert that to a single data model. A model of which all the functions like read this band, get the projection, get set the projection, all these functions will apply. So it converts any data format to a single abstract model, which can then be called in a uniform way for different other functions. So it makes your life very easy. It will appear as if all file formats are same, but it is not so. At the back end, a lot of heavy number crunching processing is happening. But for Jidal makes for you life so easy that you say file open for read data. So that way, yeah, it makes it very easy. It comes with a huge set of command line utilities. This is also very important. Now, generally Python package, if you talk about what packages you have seen, let's say matplotlib, so you import the package, you call the function, end of story, and you get your output, end of story. But Jidal is a multi-purpose thing. It has the Python command line, the Python package is there, import Jidal, read the file, write the file, etc. That is there. Apart from that, on your command line, on your command prompt, you have a huge set of command line utilities. Like, so what is a command line utility? So, for example, on the command prompt, you say cd, change the directory, or dir, to list the directory content. So, dir is a command line utility. It's a program which runs on the command line. Similarly, Jidal has a set of command line utilities which do a lot of these things which you want to do it in Python directly on the command line. So you don't need to even install Python, or for if you want to only use the command line utilities. But again, there is a lot of difference between doing things on the command line and doing things in Python. Python again opens a window to a lot of other things also, right? So you are able to connect to a GPS device from where data is coming. Then you can use Jidal to process the data, transform the data, and then you can use again Python to output the data on a LED device. So it connects you to a lot of other things. Command line is basically you open the command line, type a command, your input gets transformed to the output. So that is what command, quick and dirty things that you want to do, you use on command line. But if you want to write a bigger program which interfaces with other things, so that is where Python uh, comes in. So as I told you, primarily it is written in C and C++, but there are wrappers available on the GitHub page. You saw about 2% of the code is Swig. Now Swig is a wrapper program. It can create wrappers around a program, and abstract it for other languages, for Python, Perl, Visual Basic, R, Java, Julia, so many other languages they use Jidal. So this thing is wrapped. It's like a toffee. It is wrapped with a toffee wrapper, and now it can be used in Python. Now there is a different wrapper for Java, different wrapper for R. So there are wrappers available in all these different languages. That means Jidal can be used in any language of choice. Uh, Even JavaScript. Recently, I saw there is a Jidal JS also, which has come. So probably you can do on your processing on the browser directly. Why Jidal? Because it supports all known GIS file formats. Any GIS file format you have, which is not like very proprietary. Some vendors they will create some file format and then they'll lock it that you cannot read the file in any other software. In fact, that was the case with ISRI geodatabases. But now Jidal has cracked that also. You can open geodatabases in Jidal Python also. But there are some software vendors which play this dirty game, that they will initially tell you that no, you save it in this XYZ format, which is our format and it is the best format. And 2 years later, they will say that either you have to pay money or you have to update something linked financially you have to do. Only then you will be able to use the data. So all that is there. But anyhow, Jidal conforms to OGC standards. OGC is a global standard body which makes standards for geospatial data software. So Jidal is a OGC compliant library. In fact, it is setting standards for OGC, which means that it is open standards. Any file format can be converted to any other file format, and all these types of conversions can be done. On their page, if you look at their Jidal page, there is a link for raster drivers. Here you will see that there is a list of 159 different file types which can be opened using 159 raster file formats which can be opened in Jidal. So many of them you probably recognize things like GeoTIFF and GeoTIFF and grid files, HDF files, NetCDF files, GeoPackage files. So many are there. Earlier, some data used to come in FIT or super format, and all that is also uh, supported by Jidal. So things like ADAS, IMG, GeoTIFF, NetCDF, HDF, your web services, the data that you get from the internet, web coverage service, web map service, tile service, uh, then all these historic formats which are used for specific things like uh, mm, compression and all that, JPEG, and all your general formats like JPEG, PNG, GIF, BMP, all these are also supported in Jidal. As of September 2022, the current version of Jidal is 3.5.2. Although when you install it with Conda, you may get a version less than this. That is because there are many dependencies linked to NumPy, Matplotlib, then GeoPandas. So there are a lot of dependencies because of which a lesser version of Jidal may get installed. But whatever we do today will work with anything Jidal 3 plus. So uh, let me just give you a glimpse about the command line utilities. There are many command line utilities. Now, what I mean by command line utilities, so if you have QGIS installed in your system, you can open this software called OSGeo4W shell. This has your, let me just increase the font. Yeah. So it already has all the Jidal tools installed. So if you write something like Jidal, I think this is how it works. Oops. Uh, So uh, so Jidal info is one command line tool. It says this is the usage. It has failed currently because I have not given any file. Now let me go to my desktop. I have set of files, diff files. I want to see the information about this file, or in, let's say, this file. So I can write one line Jadal info space the name of the file and press enter, and then it will give you all the metadata about the file. What is the name of the file, what is the number of rows and columns, what is the coordinate system, what is the origin, pixel size, some metadata, the extent, left, right, left and upper and lower, and right upper and lower corners, and some statistics also. What is the minimum value, maximum value, mean, median, mode, and so on. So this is one such utility. There are many others. Another very popular one is Jidal Warp. It's a huge tool and has so many functionalities. All the details are there in this programs. If you go to Jidal Translate, you will see that these are the different arguments it can take, and for each argument, what is the default value, what it does, and all. Very good documentation is available on the Jidal homepage. So what it does, Translate converts rasters between different formats. You want to convert one TIFF file to a IMG file, or these types of conversions, you use Jidal Translate. You want to do image reprojection and warping. You want to convert from one projection system to other. You want to cut the data. You want to do these types of operations. You use Jidal Warp. You want to build contour lines from a raster elevation data. Direct, you have a command Jidal contour space the name of the raster dem, and contours will be. You want to analyze and visualize the dem for things like flow direction, flow accumulation, and all. You have a Jidal dem, a direct command. You want to rasterize a file. You have a polygon, you have a vector layer, and you want to convert it to raster. You use rasterize. You have some scattered data. You have point data, and you want to convert it to, you want to interpolate and create a raster. Then you have Jidal grid. So it also does what is called a spatial interpolation. Then you want to create a distance map. So you have points or lines, and you want to find out one pixel how much far it is from these points or lines. So you use what is known as a proximity tool, or Jidal proximity. uh, Polygonize is the opposite of rasterize. It will convert a raster to a vector. And Jidal calc, all your calculation on your raster calculator. Like you have multiple bands, you want to add, subtract, write some conditional statements, all that you use Jidal calc. So all these things, most of the things that you do with Python, with raster data, can be directly done on the command line. So you don't need to go even open a GIS software many a times. Uh, so how will you start using Jidal? I assume that you already have a virtual environment. Open the Anaconda Navigator from from your start menu, just like I did now. You click on Anaconda and open up on Anaconda Navigator. I think if you have another virtual environment, you will see Jupyter Notebook within bracket, that name of the virtual environment already written here. So in this machine, I do not have a virtual another environment. So in that environment, you search for the installed packages, and you search for Jidal. If it says there is a tick box, if there is a tick if there is a tick around Jidal, that means Jidal is already installed. If not, then you have to select all in this drop down and search for Jidal, and then install that in your virtual environment. In my case, I will try to install on the root directory itself and see what happens. Uh, Many a cases you may come across in errors while installing Jidal. In fact, uh, traditionally, or let's say earlier days, Jidal was very difficult in installing, especially on Windows and its wrappers with Python. So those were bad days. But now you have Anaconda. You can simply write one command, conda install Jidal, and it will work. Or if you want to create a new virtual environment, you can give any name. I've given here Geo. I think for you it should be Python WRM or something like that. If it is already created, great. Just activate that environment and say conda install Jidal. Or if you can do, you can create a new environment. Conda create hyphen n is the flag for the name of the virtual environment and the packages that you want. You want Jidal, you want NumPy, you want Matplotlib, GeoPandas. Just separate by spaces and you write all the name of the packages, and it will install them, and it will also install the dependencies. So Jidal has a dependency on NumPy. NumPy will automatically get installed. If you're writing GeoPandas, then it is dependent on pandas that will automatically get installed. You don't have to write pandas separately also. So I will stop with the slides with this last slide that is on the books. This is a very popular subject. Uh, Think Python is the basic book written by Alan Downey, freely available on its website. I think Python. Just search for Think Python and you will get it. Is a free book where you can learn Python. Then Chris Garrard, this lady, I have to thank her. She gave initial all the tutorials on the internet were made by her. She has written a book called Geoprocessing with Python, which is very popular. And then newer books by this publisher called Packet. So Paul Crickard and others have written this book on geospatial analysis with Python. This is also a very good book, but it covers all the different packages, including Jida. So after this, we will start with the hands-on session where we will try to see what are the different functions of Jidal. Now we shall see how to work with Jidal and Python on a Windows environment. I have installed Jidal in a virtual environment called MyENV. So in your case, you may have a different environment name, I think Python WRM. You must be seeing this prompt Jupyter Notebook, the name of your environment. Click on that. It should open in a browser, something like this. And if you have the data, it will look like this. It has a folder called raster, inside which there are multiple files, and a Python notebook by the name nwapkg2. When you click on it, it should open like this. And now let us see how we can handle or read and write raster data with Jidal in a Jupyter notebook. So let me just make this a little bigger so that it is visible. Okay. Now, so first, we need to import all the necessary modules. So here I am importing Jidal. I am also importing NumPy, and I am also importing Matplotlib, which will be required to display the images. So click on the cell and shift enter. It may take a few seconds, and but if it doesn't give an error, that means the notebook should run properly. If you get an error in this cell, you have to check which packages are installed and whether it is correctly installed or not. So the first file I'm working with is this band2 raster. So let's have a look at the data for today. Let me go back to this tab, go to raster. So there is a list3 image. This is, I think, for the Pune area. Uh, and there are three bands, band 2 band sorry 4 bands. band 2, band 3, band 4, and band 5. Then I have a small land use land cover image lulc.tif. I have a false color image fcc.tif, and I have four images of different of adjacent areas, which I will be using to demonstrate the mosaicing capabilities of JITA. So let us first start by simply opening a file. So I am just giving the name of the file. File name is equal to entire path. So this is a relative path since the notebook is kept on the desktop only. So on desktop, I have data slash raster. Inside raster, I have the name of the file .tif. Now you have to be very careful with this. The folder names, the file name should be proper, and you also need to ensure that the extension given is proper. In some cases, there may be TIFF, or maybe a single F. So you have to be careful. This R is written to escape the special meaning of a backslash. Now, as you may know, sorry, let me show you. Generally, we write some string, let's say ABC and then XYZ. So when I print it, this n doesn't get printed. Why? Backslash n is an escape sequence, which is normally in Python. If you write backslash and then followed by some characters like n or t, you will see a special effect. Like slash t gives a tab space, slash n gives a new line, and so on. So there are many such escape sequences. Now, many a times we have data like this, like folder names like data slash test slash new folder slash file name dot diff. Okay. Now, what will happen if we write the file name like this? This is not the name we were expecting. Yes. Why this happened? Because this backslash t is a tab, backslash n is a new line, and so on. Uh, and backslash f also means something. I think that is why you are getting folder aisle names. Backslash f is also not coming. So how do we overcome this problem? Simple ways: simply writing R before the letter R before the quotes. And now, if you print it, you will see the whole thing as expected is coming. So I that is why this R is written here to stop this escape sequence from getting created. Okay, so that is why this many of you may be thinking why this R is written here. The it, the it it stops this escape sequence from happening. Or the other way is you write front slash. In most Linux systems, you will see that instead of a front slash, a backslash, a front slash is used. In such a case, you don't require the R. So whichever is comfortable to you. Generally, like if we have some data, no, like if it is in my D drive or E drive or something, and inside some folder somewhere, so we just simply copy the file path from here. And if you copy this file path, it will have backslashes. Okay. So simple way is just copy the name and write an R, and that should be enough. Or you can manually convert backslash to front slash and so on. Okay, enough with file naming. So this is the name of the file. And it is just a string. So you see, file name is just a string. Then the first line is data set is equal to jidal.open. So open is the first function. Be very careful of the O is in uppercase. So jidal.open, then within bracket, the name of the file. Once I run this, you don't get any output. But let's see what goes inside dataset. So when I print dataset, it prints something within these less than greater than brackets. It says it is a proxy of a swig object. Now, If you remember the slides before this, you must have seen that Jidal is written in C++, and there is a Swig wrapper in which exposes that application to Python language. So when I'm creating any Jidal object, so the Jidal object is actually a Jidal dataset shadow object. This is the name of the class. I have created an object of this class, but it is written in C++, so it is a Swig object of this type. So Swig is helping it convert to Python. So that is what this means. The basic idea is, if you get this thing, something like this as the output, that means the file has opened correctly. Now, for example, you missed one hyphen space here, okay, and then you open the file, and then you say print data set. So you will see it prints none. It didn't give any error in these two steps. The open statement will not give any error. So you have to be very careful. You have to generally people write exception handling, a try catch block, or you can simply write an if and else. If not data set, if this variable data set becomes none, then there is a error in reading the file. Error in reading the file. If this is not none, let's say the file is correctly named and you have opened it correctly, then it will say it is not none, so file reading is success. So I hope you understand why we are writing this, because if the file is correctly opened, if there is no errors, then the data set will have some swag object. It will not be none. So if it is none, then there is an error in reading the file. So this is a easy and uniform way of reading raster files correctly using JDAL. Once the data has been read, next let us try to get some metadata information, that is information about the file, from the data set. Now data set is the pointer, or it's like a JIDAL dataset object which gets created on opening the file. It doesn't contain the pixel values yet. It is just a sort of a file pointer. So this file pointer can be used to get the name of the driver. Now, what is driver here? So if you remember the Jidal website where I showed you the raster drivers, there for each type of file, a given short name is given. Okay, so for example, let's take NV files, or let's take GeoTIFF files. This has a short name GTIFF. Or if you have a ERDAS file, ERDAS Imagine IMG file, it has a short name HFA. Okay, so each file format has a given short name. This short name to uh, is used to know what kind of file format it is. Okay, so when I run this line, dataset dot get driver dot short name, it will say it is gtiff. Okay, so that is the uh, file type, you can say. It is a geotiff file that we are trying to open. Also, we can get the number of columns and rows. X are your columns, Y are your rows. So dataset.raster x size and dataset.raster y size are the two attributes which has the information of columns and rows. So it says that the data you're trying to open has 1153 columns, 1153 rows. The third thing is the number of bands in the data. You remember you can have multiple bands in satellite data. In normal images which you take from a digital camera or a scanned image has three bands RGB, but a satellite image can have multiple bands. For example, let's talk about Landsat bands. So Landsat, again, depending on which sensor you're talking about, TM, ETM, OLI, and so on, it has varying number of bands. So the most common one or most current and popular one is Landsat 8 and 9 OLI imagery, which has these many bands. Band 1 is in the EM spectrum of coastal aerosol between 0.43 to 0.45 micrometers, blue, green, red, NIRs, where there is a panchromatic band and so on. So each band belongs to a different wavelength range, and so in currently what the file we are reading, no, it has only one band. So dataset.raster count will tell you the number of bands. If it is three bands or n bands, this variable dataset.raster count will give you the number of bands. Similarly, there are other functions like get projection and get transform, which will give you the projection and transformation information. Now, this transformation information is very important. Why? Because it is like a this get transform. No, let me print this and we'll show you what it is. It's like a tuple of six numbers. What are these six numbers? The zeroth and the third number, geotransform 0, geotransform 3, are the origin. That is the top left corner pixel. What is the starting point? Then what is the pixel size? This is given in the units, so it is currently in degrees. So it says it is 0.00225, which is roughly about 24 meters. So this is given in degrees. And then the second and the fourth value, these two values are the rotation, if there is any rotation in the image with respect to true north. So there is no rotation, so value is 0 comma 0. So this transformation and projection information is very important. Generally what we do is we save that information uh, uh, in a variable which we will use while writing the file. So till now what we have done, we have opened the file into a file pointer or a shadow data set, and we have got some metadata information, but still we have not got the pixel values. The actual data we have not touched. So that we are going to do now. So fetching the raster band. So band is equal to dataset dot get raster band and then the index number or band number. So this is a one indexed number. That means it is like an array, but it doesn't start with zero. It starts with one. First band, second band, third band. It is a one indexed number. So this file already has only one band, and I want to read that. So I'm writing one. So get from the data set, get the raster band one. So let's run this and then let's print this. So it says this variable that you've created, it's again a swig object of something called Jidal raster band shadow. Earlier it was Jidal dataset shadow. Still, it is giving us an object, but I really want the uh, data. So that will come. Now let us understand what metadata we can get for individual bands. For individual bands, we can get the data type name, whether it is byte or integer or float, 16-bit, 32-bit, whatever. That information we will get from this band.data type. Next, for a given band, we can also compute the minimum and maximum value without actually reading the whole array, whole data. So just band.compute min raster min max, that will compute the min max and store it in the two variables. So 20, so in the first band, band number 2, the minimum value is 27, the maximum value is 95. Okay, now let's verify this information whether this is correct. So to do that, I have QGIS open. QGIS is a popular open source software, and let me add the data for today. So I am going to raster, and the band 2 data I am going to add to QGIS. And now you will see here it immediately says in the layer styling panel that the minimum value is 27, the maximum value is 95. So this is what the band 2 looks like. And since it is a single band, it is showing in grayscale. Now let's go back to the notebook, and let's now come to actually reading the data into a numpy array. So reading raster data, that data is equal to band dot read as array. Now this read as array function, no, has multiple uh, arguments: x offset, y offset, x size, y size, buffer x size, buffer y size. But we have not given any. Now, why these are used? When you have a very big image, and huge image, I mean, it has something like 1 lakh rows and 1 lakh columns, and you have limited RAM. But nowadays, most systems have 4 GB, 8 GB, even higher RAM. So nowadays, it is not a problem. But earlier, when RAM was limited, so you could use JIDAR to only read chunks of the data. Okay, so skip 100 rows, read the next 100 pixels, or skip the next 200 rows, read the next 100 pixels, like that. So you could specify the offset in x direction, in y direction, and then specify how many columns you want to read, how many rows you want to read. So all that was possible. But nowadays, since we have big systems, powerful systems, we can directly read. So right now, what we are doing, we are reading one band which has 1,153 columns and 1,153 rows. So 13 lakh pixels we are able to read and keep it in the RAM. And it doesn't take any time. You just run this program and it is done. So, and it is there in the memory, this whole array of 13 lakh pixels it is displaying without any lag. So, earlier days when RAM was limited, you could specify read as array, give x offset, y offset, and number of pixels in x direction, y direction. But nowadays, if you skip all this, you can just write band.read as array and it will read the whole data into a numpy array. Since it is a numpy array, let us see the shape. Data.shape will give the shape, and it should be exactly as that of band dot uh, sorry dataset dot raster x size and dataset dot raster y size. Now we are going to use matplotlib, our good friend, to show the image. So plt.imshow. Imshow is image show. Image shows the data, and I want to show it in grayscale. So I'm giving the color map just gray. This is just to make the size bigger. So first line is to just to make the image a little bigger. So you are seeing a big image. Let's make it little small. It is appearing very big. Okay, so now we have the second band. Same thing that you were seeing in GIS software QGIS. You can also see uh, in your Python only directly in the Jupyter notebook. Now, although RAM is freely available and there is lot of it with us, it is a good idea to flush the memory, to clean the memory before you go to the next step. So if you are no longer using this file and if you're done with it, you can delete the data set, the variable data. First, assign none to the data set. That means whatever data is there, whatever file pointer is there, it will close, and then you delete the variable altogether. So this is a small thing, but it will help you clean up the memory. So if you are working with multiple big files, these two steps may be a lifesaver actually, because the RAM may get filled up immediately. So once you want to open the next image, you have to first delete the old image from the RAM, and then so this two steps are required to flush the memory, and it becomes empty so that the new data set can be opened. So till now we have seen how to read a raster data which is of single band. Now I have kept in the data for today another file called fcc.tif. FCC, as you know, is a false, stands for false color composite, which is a three band data made using NIR, red and green. So again, I am just putting the name as a string in this variable file name. Once I run it, nothing happens. Then I say jidal.open, name of the file. It will open the file, and I will make sure that the file has opened correctly by checking that the data set is not none. So it is not none, that means it is a success. The file reading is success. Let us understand what is the uh, file driver or type of file. It says gtif. Now this is also important because many a times, due to human mistakes most of the time or some computer logic, the file may get saved with a different extension. So you may have fcc.img, and you will see the software is opening, and you may be under the impression that it is a img file, but that may not be the case. So inside the file, the metadata, this thing is actually reading from the metadata of the file and not by looking at the extension of the image. Okay, so you may think we in the extension only I can see it is stiff. Why do we need to run this line? Because there may be a wrong extension. You can only get to know the correct driver by looking at the metadata of the file. So this is the authentic and correct information. The file extension may be wrong in certain cases, generally an error. So let's see how many bands it has. I told you raster count. So now it is a multi-band FCC. How many bands will it be there? Three, because three bands, as I told you, are required to make the FCC. The NIR, the red, and the green band. Let us see the three bands individually. So I am making subplots of each of the bands. Let's run this. You will see the first band, band 1, band 2, and band 3 displayed. These are the three bands which have been used to make the FCC. They have been plotted individually. How did I do this? I wrote a for loop which goes from 1 to the number of bands. So 1, 2, and 3. Each time I say get raster band I, remember get raster band takes a number which is one indexed. So this band 1, to read the band 1, you have to write get raster band 1. For this, you have to say get raster band 2. And for this, you have to say get raster band 3. So in this for loop only, I am able to read all the three bands. For each of the bands, I am saying get the whole 2D array as a numpy array. So band dot get read as array, that is coming in this variable data. Then I am creating a subplot uh, with three three images. I am just setting the title as band 1, band 2, and band 3. And then for that subplot, I am showing the image data in the color map grays. Okay, so till now in earlier lectures you may have seen this variable cmap. I have not spoken much about it, so let me show you what are color maps. And so in matplotlib we have some inbuilt or predefined color maps. What are color maps? Basically you have a list of values 0 to 1, and you want to, or 0 to n, and you want to show it in different colors. So these color palettes, you can call it, or color maps, are ready made and available to you. So plasma, let's say plasma starts from blue, goes up to magenta, then orange, and then yellow. Then there is magma and so many others. If you want a single color like grays or blues or greens, let's say you are showing some temperature, you want to show in reds, you have some precipitation, you want to show in blues. So these color palettes are ready made and available to you. And there are many others like binary and pink and autumn, winter, and then there are diverging color maps. Start with one color, go to white, and then go to another color. Some cyclic color maps, some qualitative, like you have a fixed set of values, something like a land use map. You have 10 classes, you want 10 colors. You don't want a color linear color palette, you want discrete color palette. So, like that, and then some miscellaneous color maps are ready made and built in. You don't have to uh, write extra code to get those colors. You can simply use the existing color maps. Okay, so that is what the CMAPS means. So this code simply creates three subplots displaying the three bands of the FCC. But what if I want to show it like an FCC? Simply read the whole thing. Instead of reading it as one band at a time, you say, instead of from the data set, you get raster band 1, then read as array. Then get raster band 2, then read as array. You directly say dataset dot read as array. So that is what we are doing here. I'm saying dataset dot read as array. It reads the whole file into a numpy array. And if I print the shape, it will say that it is a three band, these many rows, these many columns. So earlier we were getting only rows and columns. Now we have a three band. So this is a three-dimensional array which has three bands, 1153 rows, 1153 columns. Now for displaying using IM show, I am required to convert this dimensions like this. Put the bands to the last. So there are many ways to do this. You could use a numpy function called reshape and so many others. Here I am using a numpy function called dstack. Here I say you take the three bands, data 0, data 1, data 2, and you uh, destack it. So it converts this dimensions to 1153, 1153, comma 3. So there is no change actually between here and here, just the dimensioning of the data has been changed. And then I'm saying plt.im show data. So one, let's say if I show data, you see that the data appears, but it is a little dull. The data appears, but it is a little dull. So I read somewhere that if I increase the values, I'll be able to see better results. So you see now you can see more, but there are some pixels gaps coming. So I'm just multiplying by 2. So you can easily make out these are the two rivers which are dammed here, and this feeds the water to the Pune city and so on. Now, this becomes a very good data set for water body mapping also, which we will do at the end of this demo. Once we are done the data, it is a good idea to clean the data set so that it frees the memory. So till now, we have used simple examples to open the data set, read metadata, read one band or three bands into a numpy array. Once you have the data in the numpy array, you can perform any kind of uh, mathematics on it. It could be something like simply adding something, applying some trigonometric function, applying a convolutional filter, a normal filter, or some morphological operator, or digital processing, anything. You write something like, okay, if pixel values are less than this, then 1, otherwise 0, anything. You can, now you have a number array, you can do anything with it. Once you get the output, you want to store it back to a TIFF file. You want to output it back to a TIFF file. So now comes the next part, that is writing the data back to a file using JITAR. So now let us see how we can. First example is to use a function called create copy. This will simply take the input and create its copy. But you can still apply some changes. Like, for example, What I'm going to do here is in my data folder, which is this one, there is a folder called raster and there are no other files. Okay. What I'm going to do is I'm going to take the band 2, which is in TIFF, and convert it to an ADAS IMG file. So, how does this work? We have to first create a driver for the output file format. Okay. So, remember, I showed you on the Jidal page that the ADAS IMG file format has a short name HFA, right? So let's create a driver dot jidal dot get driver by name, and specify that I want for HFA. Get me the driver for ADAS IMG file format. So that comes to this variable called driver. Then what we do, we take the name of the source file, which is inside my raster folder, band2.tiff, and the destination file is inside my data folder. It should come as output here itself in my data folder uh, as band2.img. Let me just remove all this extra part so you can understand. It will only come as band2.img. Then what we do, we open the input file, jidal.open, name of the source file. Okay, let's run this. It says source file is a swig object of Jidal dataset shadow, just like in the beginning. Next, we will create a destination dataset is equal to driver dot create copy destination file name comma source dataset. But it gives an error saying driver is not defined. That is because this statement I did not run. I explained to you, but I did not run. So let me run these two lines. Now I have my driver ready. Now I will say DST, the destination dataset is equal to driver dot create copy. Okay, driver is this driver. The driver for the ADAS IMG file format dot create copy, then the name of the file where you want the output file, and this source dataset that you have just opened and read. So now let me read this. It gives no error now. Now let me read the first band, read the whole array. Then to perform some dummy operation, I am just simply adding the value 10 just to showcase that what change happens. Then I am going to take this data and I am going to write it to the output band. Okay. So in the destination data set, which we have just created, get the first band into this variable output band, and in the output band write array data. So this data that we have just prepared by adding 10 to the existing band. So this is a very simplistic operation. This is to just show you that you can perform any sort of operation. The only the dimensions of the array should be maintained. So if it is 1100 by 1100, the output should also be 1100 by 1100. Inside that, whatever you want to do, you can do. So once we get that output band and we write that data, the file has been created. But you may not see, I am not sure. Right now it is here, but sometimes you may not see the actual data also when you open this file. That will only come when you flush the destination data set. Only when this statement is run should you try to open this file and explore it. Okay. So now it has created a new file. First thing is that create using create copy and Jidal, we have been able to create a new file. Second, that it is of a different file format, .img. And third, we shall see what is difference between this file and the original file. Okay. So let me open QGIS. I already have the original file band2 added. This is a TIFF file which has a range of values from 27 to 95. Now let me add this newly created band2, and now if you it's it is .img. So if you go to the properties, it will say that it is a HFA or ADAS Imagine Images file. And if you open the pixel inspector, for each pixel, I want to know what was the value in both the data sets. Okay. So let's say for this value, if I click on it and if I say table, the new file band 2 has the value 54, whereas the old band has the value 44. So you see the value, old value plus 10 has got created as 54. So that is the new band which we created. How did we do that? By using the create copy command, and also by specifying a new type of driver HFA, and also doing a very simplistic operation, that is adding 10 to each of the pixel values. So if you click anywhere in this image, you will see that the old value and the new value, there is a difference of 10. Okay, very cool. So next, let us create a new file by using the create option. Okay, now what does the create option do? Create option is just like create copy, but when you were doing create copy, many things got implicitly copied without you having to worry about it, like the number of bands, rows, columns, uh, spatial reference. So many things got copied from the original file. Okay, we didn't have to worry about it. We just took the data, modified the data, and wrote it back. Okay, but what if I wanted to create from scratch? If I want to specify each and every detail, like number of rows, columns, uh, all the geo transformation options, like top left corner pixel x and y, what is the pixel size, if there is any rotation, if I want to specify everything and I want to create from scratch, that is what this code will talk about. So here we are going to use another library called OSR. OSR is part of the OSGeo umbrella, under which JIDAL also comes. OSR is for spatial reference. You want to store spatial reference, uh, then you use the OSR library. So let's import this OSR library. It should come with JIDAL. You don't have to install anything else. Let us create a driver for ADAS IMG. Let's open the source file. This source file is same as the previous one, that is band number 2. Let's open it. Let's create a new file in the data folder called newfile.img. Now I am creating a new driver. Now let us look what are the uh, inputs to this create, or arguments to this create function. It takes a path, so the destination file name path. Next is x size and y size, the number of columns, the number of rows, number of bands I have given as 1, and data type. What is the data type output, whether it is byte, unsigned integer, signed integer, 16-bit integer, 32-bit integer, floating point, double. These are the different options. So what are the different data types? Here I have written jidal.gdt underscore byte. Actually, all these data types, they have a given number, and that number is linked to some constant. So let me try and search jidal data type. It should give a list. not here, but one second. So these are the different constants which are used: GDT byte, then float 32, float 64, int 16, int 32. Then the C data types are slightly different than the others. So C data types and the normal data types and then the unsigned data types. So there are many such data types. You can, in fact, they are linked with a certain integer number also. So, or you can directly say a gdal.gdt int 16 to create a integer file. Okay. So there are many such. So depending on what you want to create, then I am setting some transformation options. I am setting the top left corner coordinates and giving the pixel size as 30 meters, and then I am creating the. So these are your transformation options. Then I am creating the projection system information. I am setting UTM to zone 11. And setting the datum to WGS84, and I'm creating this SRS, Spatial Reference System. This then is being exported to WKT so that this set projection system works. Set projection system is a function which takes the projection system like a WKT format. Now, what is WKT? WKT stands for well known text. That is the format in which, so if you simply run this, you will see that the projection system is written like a text format which says what is the projection coordinate system, datum, spheroid, central meridian, false easting, fall northing, so many other things. Okay, so all this information is stored in this SRS, and it is exported in this well-known text format so that the destination data set can be set to that projection system. Okay. Once that is done, now I have to write some data which is I have created. So I have, all the boilerplate is done. I have created a blank file which is 512 by 512, one band, this byte type, all the reference system, everything is written. Now where is the data? So for that I am creating a random integer array, and numpy has a function called random integer, and it can create array of given size. So I'm saying you create a array of 512 by 512, which will have 0 to 255 values. So once I do that, let us see what is the output. So it creates a random value output. So you see all this, it's like noise only, but these are just random values. And then that data, this variable data gets written to the output band dot write array data, and if I flush, then the output is created. So in the output folder there should be a new file. If you open in GIS, you will see noise only, but this has been created from scratch uh, using GIS. Okay, so so many a times you need to create blank rasters, or you want to create rasters with a single constant value, or you want to create a raster based on some special given circumstances or conditions. So you can use jidal.create to do this kind of job. Okay, let's go to the next part, which is stacking of bands. Many times the data comes as individual rasters, even Sentinel data. If you download, it will come into JPEG 2000 file format, and each band will be individual file. Same is the case with the list 3 data, which you get from Bhuvan, which is uh, ISRO's geoportal where you can download. So, yeah, let me also talk about Bhuvan just 1 minute. So, Bhuvan is a platform which is made by ISRO, and from where you can download various kinds of data, including free satellite data. So you go search for Bhuvan ISRO, it will take you to this website. Here there is a link to Open Data Archive. Click on that, it will open a new page. From this page you can download various things like DEM, which is very important and very useful for hydrologists. So you click on Cartosat and select the DEM product. Then you select the tile. This whole data for India is divided into tiles. You select the tiles in your given basin or watershed, and then you can download it. Of course, you will need to create a login ID and then download the data. For satellite data, you can select on resource at 1 and 2, list 3, and again select the area you are interested in. It will give you that, let's say, for a given tile, there are multiple dates data which is available. So let me click on start, select one specific tile, and say next. It says for that tile, so many date data starting from 2008 to 2019 is available. You can click on view to see a small thumbnail of that data, and then you can log in and uh, click on download to download the individual files. So that is from where I have downloaded today's sample data set. Now the today's sample data set has uh, four bands, 2, 3, 4, and 5. I will take the bands 4, 3, and 2, that is near infrared, red, and green, and let's try to create the FCC. Okay. Although FCC is given to you, but let's see how to do it programmatically. You want to create a false color composite using different band compositions that will highlight different physical phenomena. So let's put the name of the three files in a list. That list is called input files. The output file name is list3fcc.tif. The output file driver is geotiff. Let's create the output file driver. Here I am hard coding it, although it is not a good practice. I am hard coding the rows, columns, bands, and the data type. And this is my destination data set, DSTDS. Then I will go through each of the files, open the file, get the band, read the data, and take the data and write it to the output band. This output band is again getting from the output data set for each of the, so first band, I am named it index. So get the first band, write the data, get the second band, write the data, third band, write the data. Once this is done, the data is written to the file. But as I told you, you must flush the destination data set for the output to be ready. So let us now add the output. You will see a new file called list3fcc has been created. Let's add it to the GIS and let's zoom to layer. You see that the false color composite using the three bands has been prepared, is ready. Very good. Now, now some more. These are although less frequently used, but two more things that I will be showing you before we go on to water body mapping is first is creating a color table. Now, why do we require a color table, or what is a color table? Now, imagine the input file is a land use land cover file. Let us add it to GIS and let us first visualize the problem. Then we will see uh, why we need a solution for that. So I have a land use land cover file. Generally, a land use land cover file. This is a very small portion of Dehradun city actually. Uh, 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 this is Dehradun city actually. These are the Tarai forest just south of it, and then the Masuri hills, Shivalik hills to the north of it. Generally, a land use land cover is a discrete integer file. That means if you click on this pixel, it says it is of value 13. If you click here, it says 9. If you click here, it says 2. So what are these numbers? 2, 9, 13. They generally are linked with some class. So 13 may be urban, 2 may be forest, uh, these values here, 9 may be cropland, and so on. So each of the unique values are linked to a number, a class. Each of the unique numbers are linked to a class. Now, when I add the data, it appears in black and white. It doesn't convey a lot of information. Uh, for a for a non GIS user, he'll not be able to understand what this data is. So, wouldn't it be best if we store the data such that we store the color of each pixel along with it? Like I want the urban areas to be stored. When I add the data, it should come as red. I want forest to appear as dark green. I want the cropland to appear as yellow. I want the river to appear as blue. So on. So given a pixel value, I can assign a color to it. So how do we do that? Is what is creating a color table. So we take an input and we create a new output. So let's open the file, create a driver, because we are going to create a copy of the input file. So we will create a copy and create a destination for the destination file, and create a destination data set. In the destination data set, we get the first band and call it the variable band. Now we are creating a variable called colors, of a which is an object of this function color table. Jidal.color table will create a new color palette. In this color palette, I am saying colors dot set color entry 1 comma 56910. Now what is this? So what I'm saying is, for this pixel value 1, I want to set this color 56910. Any guess what this is? This is a RGB code. Okay, now very simple, without internet also I can show you. If you open Paint 56910, okay, if you open Paint and if you say edit colors and you write these numbers here, oh, sorry, I forgot again, 569 and 10. So this is a shade of green. Next color is 8 106 16. 8 106 and 16. This is another lighter shade of green. So each color, on this red or green or blue has a given top three digit combination. So this purple color is 115, 10, 137. So any class that you want to show with one color, you specify here. I want to specify that the class by number 1 should be this color, 2 will be this color, 12 will be this color, and so on. 194, 79, 68. So the class number 12 will be shown as 129, 74, 68, which is I don't know the name of this color, shade of something like light red or brown or something. Okay. So the idea is, I am specifying that when the new file will be created, the pixel values will be associated with these colors. And most GIS softwares respect these rules. Okay. So in the output band, this is the output band. Remember, from the data set, I got the first band. In the output band, I am setting this color table. Colors is this color table that we created, and we set all the entries. Oh, I'm not run. Acha. And then I am setting a interpretation that it is a palette, and then I am saving. The file is saved. I'm just clearing the RAM. So let's run these statements and let's see the output. Okay. So I showed you this file, uh, which is all grayscale. But now, with setting the colors, I have created a new file by the name LULC map. Remember, the name of the output file was LULC map. So let's see the output file in GIS again. Wow. Now, same information, as soon as I add it to GIS, it is coming in colors. So I have given different classes. So these are my forests, these are my croplands, urban area, and other land use types. There is a water body here. So everything is appearing with the color directly. I don't have to, and you are also having the entire legend. So I don't have to go in GIS and then set the color for each pixel value and so on. So this is although not frequently used, but a very important and interesting thing that you can do with JIDAL. The next part is mosaicing images. I have four images which are of the four corners. They are just adjacent to each other, and I want to mosaic them and create a single file. Okay. Many times you have a larger area which doesn't fit into one satellite image. You may require two or more satellite images which are next to each other, and you want to mosaic them. So what you'll do, you'll open a GIS software, and then you'll do all that. So without GIS software, also in Python or in the command line, also you can do it. So I told you in the lecture that there are many command line functions. So I'm going to use that command line function, but in a Python way. Okay. So JIDAL warp, that function I am going to use, but now in a Python manner. So here, what I am doing, I am simply making a list of all the files in that folder that I have. So if I print this file names, you will see that it is a. Let's create a list and see if so it says that there are four files: bottom left dot tiff, bottom right dot tiff, top left dot tiff, top. I have named it like this so it becomes easier to understand. Let us add some of them and see what I am talking about. So let's take bottom left, add it to GIS. So it says this is the file. Okay. Let's zoom out a little bit so that I think I have to turn off the others. So this is the bottom left layer. Okay. This is the bottom left layer. Now let me add the bottom right. So this is a separate file. As soon as I added, you see it comes right next to it. So this is a separate file, but they are both linked to each other. They are of the same geographical location but just adjacent to each other. Okay. Then you have top left, so it comes here. I have just named it like that so it becomes easier to understand. And the top right. So what I want to do is I want to take all these four files and I want to mosaic them, that is the GIS operation, and create one single file. Okay. So how do we do that? uh, so we open each of the files, we enumerate through each of the files, jidal.open, read the data, and then, so here I'm just plotting it. uh, I'm just plotting the four images, but it is not showing. Okay, never mind. Okay, let me write plt.show. Maybe it is very big or something. It is not showing. Never mind. The point is that I have opened each and every file, and that data set I am appending to a empty list. Remember, data sets is an empty list that we created in the beginning here. It's an empty list, and after this for loop, I have opened each and every file made a data set and appended to this empty list. So at the end of this loop, this data sets uh, variable is a list which has okay, maybe I have done something incorrect. No, so this was causing some issue. Let's delete that. So now I can see my four subplots. These are my four images that I want to mosaic. And after this, I see that the data sets is a list of four data set shadows. Okay. Only these four are required. This list is required. This Jidal warp function will create this output file, mosaic.tiff. It should create inside the data folder. So data slash mosaic. This is the output file name. This is the input, the four data sets, and the output is HFA. Okay, let's convert it to GTIFF. And let's run this and let's see what we get as the output. So it says it has joined the four images. Now let us see it in GIS whether it has actually done it. So in the data set, I have one new file called mosaic.tiff. Let's add it here. So you see it has joined the four files into one single file. Okay. So this is very interesting. This is very important when you have thousands of files and you want to mosaic them. Doing it with GIS and all, it is very cumbersome. You can write a for loop and simply uh, uh, write a for loop to open all the files. All these are not required actually. These are just to plot. Let me comment this, put a comment here. These are required. These or next statements are required for plotting only. So these are not required actually. Just open the data set, put it in an empty list, and use the warp function to create the output. Okay. So now we have successfully mosaiced all our four images. Now you can pause here and go through what we have done till now. Now after this, we are going to do a real life application of the entire raster handling that we have done till now. So the application that we are targeting is water body mapping. Now we want so many satellite images are there, and identifying service surface water is a very important task uh, to understand water availability and so many different applications. So uh, here I am going to show you how to do it using satellite imagery. Now, list three images are freely available. Uh, uh, Cloud free at some intervals. If you want at regular intervals, of course you can purchase it from NRSC, but some of the free data, as I showed you, is available from Bhuvan. So you can go to that website and download for your area and all that. So once you download a file, you will see it's a zip file. When you unzip, it will come. It will show you that it has these bands: band 2.tiff, 3.tiff, 4.tiff, 5.tiff. There are four images actually. Each of these are taken in different spectral bands. So spectral band 2 is zero point 0.52 to 0.59 micrometers. Spectral band 3 is zero point 0.6 to 0.68, and so on. And these correspond to different spectral zones. So this is green, this is red, this is NIR, and this is SWIR. So 2 belongs to green, 3 is for red, 4 is for NIR, 5 is for SWIR. Now, water bodies are generally identified by using an index called the Normalized Difference Water Index, or NDWI. There are two well-known formula in literature for NDWI. The first one is green minus NIR divided by green plus NIR. The other is NIR minus SWIR divided by NIR plus SWIR, where G, NIR, and SWIR stand for green band, that is band 2, NIR, that is band 4, or SWIR, that is band 5. So if I have these bands, let's say I'm taking the first equation. Let's focus on the first equation. G and NIR. G is green, band 2, NIR, which is band 4. So if I open band 2 and band 4, and if I perform this mathematics, okay, so green is what? 2 minus 4 divided by 2 plus 4. I will get my NDWI. From that, we will see how we can further exactly identify the water boundary, uh, so on. So let us apply the first formula. Let us take the file in the green band, that is band 2, NIR, which is in band 4. Open the file and read it into an array. In one line, I have directly no getting banned business and all. Just one line only, you can open the file and read it into an array. This is not advisable. Okay, writing this way is not advisable, but this is quick and dirty. I know that the file small is small, it has only one band. So small files, this will work. For large files, this is not the advisable. So I have my green data, I have my NIR data. Let's write the NDWI equation, which is green minus NIR divided by green plus NIR. So I get my NDWI. Now let us see how it looks. Okay. So when I plot it, it looks like this. So you see all the water bodies. Remember this image? This is the same area. Okay. Let's look at the FCC. So this is the area. Okay. So these dark parts are the water bodies. Okay. This one here, this one here, this one here. There's one small here, and so many others. There's many small water bodies in this area. Okay. So once we create the NDWI, we see a grayscale image. That means the minimum value is 0, maximum value is something like 4. And we see the higher values are appearing in white. The water bodies are appearing in higher values. That means anything which is above a certain threshold, let's say above 1 or above zero point 0.5, is water. Okay. But we are also seeing some dots here. Okay. These are all noise. So, how to reduce noise? We can run a smoothing filter or a low pass filter. Gaussian filter is such an example. Gaussian filter is built in SkyPy, which is there in Anaconda, so you don't have to install a new package. So in SkyPy, there is a submodule called n-dimensional image, ND image, which has a function called Gaussian filter. I am running it over NDWI. This sigma is for how much amount of smoothing you want. If you write one, less filtering will happen, two more, three, even more. So like that. So I tested with one. I saw that the output still has some noise. Then I gave two, and then it appears that the noise has reduced quite a lot. Okay. If you smoothen a lot, then some water body may get skipped also. Okay. So this is something that you can experiment with. After smoothing, I saw that the new filtered NDWI has a different minimum and maximum NDWI value. Okay. Now let us plot the histogram of this image. Okay. I hope you understand what is histogram. So histogram basically tells you the pixel values on the x-axis and how many times it is occurring. Okay. So when I plot it from 0 to 1, I see a peak here. That means this is where all the water bodies are actually. Okay. So anything which is uh, l- less than a certain threshold here, less than a certain threshold is not water body, anything above is water body. So just by manually looking at it, I understand that it is somewhere between zero point 0.5 to zero point 0.6. I have taken 0.58. Again, this number can be uh, No, this is not by uh, create a binary mask with a manual threshold. This is done by manually understanding that maybe the threshold is 0.58. So after you run a 0.58 filter, you get a binary image. So anything which is less than zero point 0.5, uh, uh, anything which is less than zero point 0.5, okay, this is all becoming 1, the rest are becoming zeros. Okay, so I have plotted this, so now you can see all your water bodies are in 1, the rest are zeros. So the rest I am masking out. Okay, I am I am writing a line, water is equal to np. Numpy has a function called, has a data type called masked array. So I'm saying numpy dot mask array wherever this binary mask is 0. So wherever this is 0, we will put mask it. That means it will become transparent. Okay. Now what I am doing, I am simply taking the FCC and I am plotting it along with the water mask. So this is the FCC, this is the water mask, and if I overlay this with this, then this is the output. So you can clearly see that we have exactly covered the water. We have created a water mask. Now from this we can create the water area, we can save it as a new file, and so many other things. There is so many experimentation you can do. You can try to write the same things, just use the second ndwi formula. Remember, there are two ndwi formula. So you, instead of reading green and NIR, try reading NIR and SWIR, which is band 4 and 5. And then you see what does the histogram look like, where should you put your threshold, and whether you get a better approximation of the water bodies map. What should be the threshold and whether the output is even better. Now, some people also don't do the threshold thing manually. They want an automated way to do it. So a lot of literature suggests that we should use this Otsu's method for interpolation. It is built in several libraries. I did not find an implementation, direct implementation, like a direct function in NumPy or SkyPy. So there is one in Skit Image, there is one in OpenCV. So you'll have to install these libraries, these new other libraries. Like this one is Skit Image, which is an image processing library in Python, or you can also use OpenCV. So in Skit Image, this there is an example given here how to use Skit Image to find. So this will directly find. So this one line, no, if you give the NDWI value here, it will directly find the threshold for you. So using that threshold, if you create your binary, you will get the water body map. So there are lot of research can be done how to find out, then seasonal variations and effect of shadows, and so many things can be done with this. So what did we learn today? We saw how to work with rasters in Python, how to read it, how to write it, uh, how to do color tables, mosaicing, stacking, and finally a real world application on water body mapping. I hope you learned something, and if you have queries, please feel free to write on the forums or send me an email. Thank you very much.